Our next two sample problems are going to focus on Gibbs free energy, which is kind of the new thermodynamics term that we're discussing in this chapter. We've already seen entropy discussed a lot in this chapter, and we've previously learned about enthalpy. So what we're going to see now is that Gibbs free energy, which we assign the letter G, is really a combination of enthalpy and the temperature-dependent entropy aspects. And what we'll see is there's two ways that we can calculate free energy, and we'll go through two sample problems for each of those. One of them uses what we call the Gibbs free energy equation, which is delta G equals delta H minus T delta S. So we can calculate free energy by considering both the entropy and enthalpy components. Alternatively, because Appendix B also has a column of delta G of formation values, we can actually use an equation that's very similar to what we already discussed and used for enthalpy and entropy, and we can use that for calculating delta G. Now, just to make sure there's not any confusion here, because this nomenclature does kind of change back and forth in your book. Sometimes you'll see delta G system, sometimes you'll see delta G reaction. They're both referring to the same thing. If our system is a reaction, then that's what we're talking about, is that chemical reaction. One thing that we will have to make sure we take a look at, though, is if we see that little circle, it looks like a degree symbol, we call that naught. This is delta G naught. That refers to what we call standard state. We'll get to that a little bit later on, but for right now we're going to consider delta G naught values, and again, that's what we're going to see for our Appendix B, is all of these have that little naught symbol there. So we'll talk about a little bit later what that means, but it is important to note whether you have that little symbol there or not. Okay, so this problem and then actually the one following it are going to look at the same chemical reaction, but we're going to calculate delta G in two different ways. The first way is we're going to calculate it using enthalpy and entropy values, and then we're going to use the delta G equals delta H minus T delta S equation. So again, this delta G equals delta H minus T delta S. We're going to use this equation in this case to calculate for delta G, where we're going to separately get this guy from Appendix B, and then also work through and figure out delta S from Appendix B. So to go ahead and do this problem here, I'm just going to rewrite my chemical equation for KLO3 solid. If we heat it, we get 3KClO4 solid plus KCl solid. So what I'm going to do is I'm going to simultaneously grab both delta HF and S values. So delta HF and S values. Again, my delta HF is going to have units of kilojoules per mole, and I'm going to have joules per mole Kelvin. All right, so I'm just going to translate all of the values that I got from Appendix B here. So a lot of errors that can be made in here are not putting the right value under the right substance, not looking up the right value because you looked up the wrong phase. So lots of ways that you can make silly little mistakes here, not carrying the correct coefficients through, maybe not having a balanced chemical equation to start. So delta H system, again, products minus reactants. I'm going to put my products in brackets. So I'm going to have 3 times minus 432.8 plus 1 times minus 436.7. I'm going to subtract my reactants. I only have 1, 4 times minus 397.7. Carry out this math, you get the delta H of the system as minus 144 kilojoules. Delta S for our system. Again, products minus reactants. Mathematically, this is minus 36.8 joules per Kelvin. So we're going to get to this again later, but I'm going to kind of introduce it early and often here so that it makes a lot of sense when we get to it later. The enthalpy for our system is favorable because we have an exothermic reaction. The entropy for our system is unfavorable. It's positive. Now, we couldn't have necessarily predicted that looking at what we have going on here. We don't have any moles of gas or anything, so this one may have been a little bit difficult to look at and predict. But what we do know is if we have an unfavorable entropy, we must have a favorable enthalpy to compensate. We're never going to have a situation where both of those are unfavorable. That reaction will never be spontaneous. So we calculated our delta H and our delta S values, and now we're going to go ahead and put this in this equation. Delta G is equal to delta H minus T delta S. So we're going to have, and I'll go ahead and I'll convert this guy into joules. Well, you know what? Let me go ahead. I'm going to convert my this guy into kilojoules, just so we can see that that works just as well here. So my delta H, again, is going to be minus 144 kilojoules, minus my temperature is going to be 298 K. And then my entropy is minus 36.8 joules per Kelvin. And then I've got 1,000 joules is 1 kilojoule to convert to kilojoules. Make sure that you use the right relationship here. Very common mistake is that people will put 1,000 on top rather than the 1,000 on the bottom, and you're going to be off by a factor of 1,000,000 then, because you kind of had that. You were supposed to have it on the bottom, you did have it on the top, and so the net mathematical effect of that is you'll be off by a factor of 1,000,000. Work through this math here when we get minus 133 kilojoules. Now, for this reaction, and we'll see this kind of play out in a little bit, we knew that entropy was unfavorable. We knew that enthalpy was favorable. But what we'd have to see is we'd have to see if this would play out such that the temperature was such that we still ended up with a negative value for delta G. And maybe I haven't mentioned this yet, but to make sure to mention it, if we want a reaction to be spontaneous, delta G must be negative. So that's kind of an important component to remember. So we can see here that our free energy is negative, so this reaction at this temperature is spontaneous. And let me just kind of throw out something here. We'll get to this in a little bit more detail later, but let's see if this makes sense. We had a helpful enthalpy term here, and we had an unhelpful entropy term, right? Because subtracting a negative number here means this is going to be adding to and detracting from this, right? We went from minus 144 to minus 133. This term wasn't helping. Does it make sense that if this temperature term keeps increasing and increasing and increasing, eventually the weight of this T delta S term will be such that when we subtract it off of here, which really means we're adding it, it's going to overwhelm this such that delta G becomes positive. And then the reaction's non-spontaneous. So one of the things that we'll get to is when we have one of these situations that I call a win-lose. Favorable enthalpy, unfavorable entropy. We have a temperature dependence. And when entropy is unfavorable, we want to diminish its contribution. So in that case, this reaction will be favored at low temperatures. If we increase the temperature, now entropy in terms of a mathematical weight here becomes more significant, such that it will overwhelm our enthalpy, which is favorable, and we'll end up with a delta G, which is positive, and then that reaction is non-spontaneous. Okay, we'll get to more on that in a little bit. We're going to move on to our next problem now.